Good morning, everyone. Welcome to the European American Collaboration in Wind Energy monthly webinar series on wind energy research. This is part of a project run by Jakob Mann of Danish Technical University. I help him run this webinar series. I'm Sue Haupt of the National Center for Atmospheric Research in the US. And today we are pleased to have with us Emmanuel Brandlert of UMass Amherst. And Emmanuel is an associate professor of mechanical engineering at UMass Amherst, focusing on multiphysics, aero, hydro, servo, elastic modeling of wind turbines using mid to low fidelity models and open source tools such as OpenFast. Before that, Emmanuel worked at the National Renewable Energy Lab, Ørsted, and Technical University of Denmark. Emmanuel, you have the floor.
Thank you so much for the introduction, and thank you for everyone for joining today. As my title indicates, there's I'd like to present two applications to what I call low fidelity models. So I have a digital twin application and some kind of stochastic uncertainty propagation application. So hopefully that makes the talk a bit, you'll have two different flavors, maybe slightly more entertaining. And this is work that I've done with my co-authors at NREL, where I was before, and while I was transitioning to UMass also. What do I mean by low fidelity models? First of all, maybe one of the most complex examples that we have is a floating wind turbine in our world. We have, depending how you count, of course, but thousands of degrees of freedom. We have external loads from the wave, the sea current, the atmosphere. So quite a complex problem. And my approach, and a lot of people's approach, is to simplify this problem. And the reason for doing this is when we model this, we want to minimize our computational costs. So we want to have faster computational models. By simplifying the model, we can also gain some physical insights. We capture maybe some simpler physics, and maybe we can explain 90% of the outcome. So that's easier than when we have too many degrees of freedom. Then it's hard to pinpoint what is the source of what. And yeah, my third point is things become achievable because, again, it's related to this computational cost, things that maybe you couldn't run real time. Now all of a sudden you can run them in real time. So I have two applications of simplifying a wind turbine model and then playing with that model if you want. The first one is, as I mentioned, related to the stochasticity in the inputs that we have. The wave is highly stochastic. The wind is stochastic as well. So how to account for this? And my second application is digital twinning, which is a buzzword at the moment. And it's all about everyone has different applications, but trying to follow the life cycle of an asset by having a virtual asset on the side. And that's what I'm going to start with. I'm going to start with digital twins. So to give you a bit of background, the question I like to ask at this stage is, imagine if you build a floating wind turbine somewhere out at sea, and you're trying to figure out how is the structural health of this turbine. Is it doing okay? Is it going to break? Does it need maintenance? So obviously we have some measurements on the turbines. There's standard sets of measurements like rotational speed, pitch angle, acceleration of the turbine. Those are standard measurements. What we could do to figure out if the turbine is doing okay is to add more measurements or process those measurements. Those are two different things. You could process the existing measurements or you can add more measurements. Another thing we typically do is we go monitor the turbine either by boat or by helicopter. And then we do a visual inspection, but all of this can cost extra money. So additional sensors or visits to the inspection visits can be extremely expensive. So the idea, the vision for this digital twin is, can we use our modeling expertise to provide tangible information for the operation and maintenance without adding expensive instrumentation? So within my drawing scheme, that would be using the computer, the existing measurements, and doing something more with it. So it's really, we have existing measurements. Let's not add any more measurements because those are expensive. But let's do some magic with our knowledge of the turbine and those measurements to try to estimate the health of the turbine. So that's the vision. Another sketch of the vision is we have those measurements. We want to process them in what we call a digital twin, which is a software that runs in the cloud. Ideally, we would like the software to run real time, so online, something that can give you information right away. So that's where the low fidelity models comes in, because we want things to run fast. And the output of this digital twin is some data, some kind of data, ideally, that can help operators to decide whether or not to do maintenance or optimize at least the maintenance costs. And so within this digital twin, and that's more or less the outline of this presentation, is first, I'm going to develop those reduced order and linear models. Then we're going to try with those models to estimate states, which is basically in a structural degree. Those are going to be the structural degrees of freedom of my system. And then with those states, we can try to get some useful metrics. And that's really something that I could work more on this, but because useful metrics, it's a big word, and there's a lot of things that can be behind it. We're going to apply this to an existing asset. So we have the TetraSpar prototype that has been shipped off the coast of Norway that is operating. And we had a nice partnership with Steesdale Offshore that has also a partnership with many entities. So we use data from their prototype for this application. And I'll dive into more what are the data. But it is a big prototype, 130-meter diameter, 2.3 megawatts. So a very large structure. So first, how do you get reduced order model of this structure? And I should say reduced order model is a term that is used a lot in the finite element world. I'm using it slightly in a different way. I'm just mentioning just lower degrees of freedom. That's the way I look at it. And DOF means degrees of freedom in my slide. So how do we simplify it? The approach I use is fairly standard. So the blades are obviously very flexible, but the next object in line is the tower that is pretty flexible. So modeling the turbine, the tower with only 1 degree of freedom. So instead of having an infinite degree of freedom for a beam, we model it with just the first mode shape, if you want, of this tower. I don't really like to use the term mode shape. I prefer to use the term shape function, because it is really, that's just a way to simplify the problem. And we use this shape function to reduce the dimensional space, or to separate time and space. So we only have 1 degree of freedom for the tower. We consider rigid inertia for the nacelle and the rotor. So this is clearly a simplification. And I have 2 degrees of freedom, then this tower bending, and psi is the rotation of the shaft. And then 6 degrees of freedom for the nacelle, for the substructure, rigid body, rigid inertia for the substructure. And then we have the loading that comes into play, and we have the hydrodynamics that is quite complicated, but we simplified it into a point load. So we try to extract the linear mass, stiffness, and damping matrix from the aerodynamics. And the mooring line is also point loads. In our case, we simplify it to the center of mass. So a lot of simplifications. For the aerodynamics, actually, we're not going to simplify it right away, because we figured that the aerodynamics will have a very strong impact in our system. So we choose to deal with it a bit later. But at the end of the day, we reduce this system to 8 degrees of freedom, shaft rotation, tower bending, 6 platform degrees of freedom, and some rigid body loads for the mooring and the hydrodynamics. And we did this in 2 ways. We can do this with OpenFast, and we've also developed our own internal tools to to do this kind of reduction ourselves. I won't go too much into those details. Once we have this simplified model that is still nonlinear to a large extent, we linearize it. So we put it into a form AX plus BU, where X is our state vector, U are our inputs. And to do this, again, we still have those two approaches. We have OpenFast that can do linearization, and our Python tools that can also do it, but they can do the linearization analytically, as I'll come to explain. OpenFast mostly does linearization numerically, which means you introduce a small perturbation of your state. So for instance, you displace your structure by a small delta X. You look at what is your force. Then you displace your structure in the other direction. You look at what are your forces, and then you do a finite difference, and you get an estimate of the stiffness. So that's really the idea behind the linearization that is used in OpenFast. Whenever possible, OpenFast use analytical linearization. When we know exactly the form of the model, we can try as best as we can to do, we compute those gradients analytically. And then for the structural model of our second Python approach, we have it fully analytical, which gains some time when you want to linearize. And it gives you more accuracy because when you do numerical differences, you're a tiny bit sensitive to this, how big is the delta X. So at the end of the day, we have this reduced order model that now we've linearized, and I'll explain why I linearize it is because I'm going to be using a Kalman filter, and Kalman filters on their simpler form, they need a linear model. So the next step is to try to do the state estimation, what I call also extrapolation and virtual sensing, which is trying to combine the measurements and the models that we have, this simple model that I was describing, combining them to get something useful out of it. And combining a model and measurements, that's exactly what a Kalman filter is doing. And Kalman filters try to find what is the most likely state that minimize the error between the measurements and the error that is also inherently our model has some error in it. So it's really trying to optimize the errors between those two. It gives us the most likely states. So a simple example for this, and that's an example that we use actually in this model, is we try to estimate what is the aerodynamic torque using only the knowledge of the power and the rotational speed. So that gives us the generator torque. So that's QG, the generator torque that we have here. And we're trying to figure out what is QA, the aerodynamic torque on the other side of the shaft. Yeah. The equation of motion for the shaft is fairly straightforward. It's just inertia, moment of polar area, moment of inertia, times the acceleration of the shaft is equal to the difference of the torques. And we can put this into state space form, but it's fairly standard, except here what we did is we added one extra row. We add one extra state in our state vector. Typically, you just have psi and psi dot in your state vector. Here we added QA. And this means that on the other side, I have a QA dot. And in that case, I have absolutely zero dynamics. So I'm kind of relying on the Kalman filter with very minimal or basically no knowledge of the aerodynamic torque. I'm just giving this to the Kalman filter and hoping that it will find the best aerodynamic torque suitable. This kind of hack, putting a force in the state vector, is referred to augmented state space. It's usually best if you have a model for the dynamics, but in that case, I don't even have a model. I do have an output equation. This is a detail, but the output is what we measure. So my color scheme here is like green is the measurements. So we know we measure the rotational speed, psi dot, and more or less the generator torque. So we can relate this to our states. So at the end of the day, how does this look like? This is an example from the simulation world where in blue, I have run a simulation with a bit of a crazy wind speed that ramps up, a turbulent wind speed that ramps up and ramps down. And this is the aerodynamic torque as function of time for 10 minutes. And in blue is what we have from the simulation. And then if I give the rotational speed and the power to this estimator, we can estimate the aerodynamic torque with fairly good accuracy. So that's an example of using a simple model to do some estimation. We also have a wind speed estimator in this digital twin. And to do this, I think it's a fairly standard model. We do a database of torque and thrust as function of wind speed, rotational speed. And we also have it as function of the platform pitch for offshore, but I didn't put this into the slides here. And the idea is once we get the generated torque, the aerodynamic torque from the Kalman filter, we can find what is the wind speed by just doing a table lookup. Okay, that's the principle behind our wind speed estimator. And then we can get the thrust force. Once we know our rotational speed and our wind speed, we get the thrust again from the tabulated data. Then, we have wind speed, we have aerodynamic torque. We probably want to have other metrics. And the metrics we looked at right now was trying to figure out what are the loads in the tower. What are the section loads, or like the tower bottom moment, tower top moment? And OpenFast can give this to us pretty readily because it already has linearization about all kind of input and output. It has the relationship between all the inputs and outputs that you have in your model. So we can go and extract this information. It's basically a given row of a matrix that's going to give us, through a product with the states and the input, states and input, we can get any kind of output we want. And in particular, we can get the bending moment. The other approach that we do in our Python tool is we actually try to integrate the section loads, and then we go back to all the details of how the section loads are computed and the influence of the inertia of the nacelle. And so that's how, by just having some information on the nacelle and the thrust force at the tower top, we can figure out the section load along the tower. So at the end, we have those measurements. So the measurements we have for the TetraSpar model are X and Y, which is basically GPS location of the turbine, phi Y, phi Z, which are inclinometers that gives us how tilted, how pitched and rolled the turbine is. We have the rotational speed, some acceleration at the tower top, generator torque, and the pitch angle. Those are the only measurements we are using. We're combining it with our model. We do some virtual sensing on it. And at the end, our main output at the moment is to try to get the section loads along the tower. We also get wind speed and thrust, but really what we're after is maybe the tower bending moment. And ideally, once you have this, you can try to look at what is the fatigue on on the tower, for instance. Some results. So first, we worked in the simulation world. So we didn't use the measurements from the TetraSpar. We just simulated the TetraSpar with OpenFast. And because that's the nice sanitized environment, so it's a bit easier to figure out what's going on. And this is a comparison of aerodynamic torque, thrust, tower top displacement, and tower bottom moment at the end. And in blue, you have what we think, what we know, the signal R's are from the simulation, and in orange is what the estimator is doing. So overall, pretty good estimation. You can clearly visually see some differences. We have done some quantitative analysis as well. But moving on to the real life application, we use 4 days of measurements from the TetraSpar. And then we use the real measurements from the turbine. And the beauty of this is a prototype turbine that has extra measurements. So that's what I'm gonna. Usually you don't necessarily you don't have strain gauges everywhere, or they're gonna fail after some time. But in that case, they place special attention to having many strain gauges and many additional measurements on this prototype, which gives us. Then we can validate our model, our estimation. Maybe in real life, there won't be a strain gauge here, but now we have a strain gauge, so we can compare against it. And so that's an example of a comparison. In orange is the estimator, in blue is the measurement. And in that case, the damage equivalent load is estimated with a very small error. but there are cases, I'm not gonna lie, you know, there are cases where even though the time series look kind of similar, we have maybe a slightly higher standard deviation in our estimate, and the damage equivalent load ends up being 32%, no, 33% higher than what the measurement is indicating. So that's the kind of spread of results we got with this model. Sometimes very good, sometimes not so good. But I feel like this is about how good you can get in estimated damage equivalent loads. So as function of wind speed, those are our 500 time series from measurements. This is the error in percentage when we try to estimate the wind speed. And this is the error when trying to estimate the thrust, so below 20%. The error in trying to estimate the tower bottom bending moment. And yeah, the spread is between plus or minus 50%, but on average, maybe plus or minus 15. And then the tower top moment is about the same kind of range. So overall, I call this some encouraging results. I think it's not easy to estimate damage equivalent loads. You have a lot of frequency content that can contribute to those damage equivalent loads. So capturing everything is quite tricky. But I think we managed to get some of the quantity of interest with 10-15% accuracy. There's definitely room for improvement in increasing the complexity of the model, trying to estimate the health of other components than the tower, like the shaft, the gearbox, the substructure, the floater. But this is our first step. So this was posted on the NREL repository back then. It's not maintained anymore. And otherwise, we also have our Python tools in a different repository. So this was the first part of my talk, and I think I could take some questions, maybe. I don't know if you take questions. Oh, but it's recorded, right? So
yes,
maybe I
it's
should jump.
recorded. Does anybody have a pressing question they'd like to ask now? We usually let them wait until the end.
That sounds good. That sounds good. I'll keep going. So yeah, this is the intermission. So clear your mind of all of this. I do have a cat video. I'm a cat person, I guess, just to entertain you of what I think could be going on inside of a wind turbine generator sometimes. I'm just amazed of how fast those cats go. So another application to low fidelity models. We want to dive, the question we had in mind, I'm going to dive into what the objective was. It's the fact that we deal with renewable energy system. We don't know, we have uncertainty on our fuel. The inputs we are dealing with are highly stochastic, which make the energy production difficult and assessing the reliability also difficult. So for instance, turbulence, you know, could make our blade break, and our tower. We have a lot of examples at the moment in the news of turbine failing. And so there's definitely understanding the source of stochasticity is different. To be fair, there's stochasticity in the manufacturing process, and probably that's also one of the main causes for those failures. But still, how do we assess for this stochasticity? Nowadays, our approach is brute force. We run tens of thousands of simulation, which illustrate this way. For instance, the forces, that's going to be my input in this case. We have many samples of forces. From those forces, we're going to get different displacement, different velocities. And then we can look at the statistics of what is the displacement, what is the probability density function of my displacement and my velocity. So usually we do this on tens of thousands of simulations. The approach I suggest is instead try to account for stochasticity directly. Is there a way to do this? We know we have as input, we know the probability density function of our input usually, And can we get directly the probability density function of our output? Obviously, those probability density function, we use them for some analysis, like fatigue analysis. We can iterate in our design if we are not happy with the results from the fatigue analysis or just the statistics of our the response of our system, and also to estimate how much energy we're going to produce. But so the approach is trying to basically not do a brute force and go around this loop and go from probability density function to probability density function directly without doing sampling. So again, our models, you know, in the big system dynamics world, this is typically how our models are represented. Similar equations that I had in my previous talk with a general state and output equation. My color scheme is the same. Blue are my states. Green is the input and orange is the output of my system. So if you know a time series of the input, if you know those equations, you can integrate it, get the state vector as function of time, then you can get the output as function of time. This is just a simple relationship. If you do this multiple times, you can get the statistics of your states and outputs. But this is when we do it, the brute force approach. So how do we avoid this? There's several paths forward that we identified. The first one is stochastic linear theory. The second one is stochastic differential equation, also called Ito equation. The problem with this one is it is stochastic, but it is kind of a brute force approach for as far as I can see. And the last approach is the Fokker-Planck equation, and which is basically what we want. And so what we're going to do is we're going to introduce those methods and then compare them on a simple reduced order model once again. So stochastic linear theory is very close to linear theory, but it accounts for everything has a stochastic process behind it, basically. So it is presented in a way that is slightly different than when you do linear theory in general. But again, it's linear, so we linearize our system into some A, B, C, D matrices that relates to states and inputs. From those matrices, we can compute transfer functions. Those are transfer function matrices in general. So the relationship, this is like a bit of a abstruse notation. I'm dividing two vectors here. It's a bit awkward, but we have a matrix G, which is our transfer function matrix from input to states, and H, which is from input to output. There's simple linear algebra based on those matrices. And what this gives us is we can get the power spectral density of the output as function of the power spectral density of the input by just multiplying by this transfer function matrix. So, which is great. This is almost what we wanted. We have the spectrum of our input, we get the spectrum of our output without having to run any simulation. A simple example that's the example I'm using in this talk. It's very simple. I have an input tower top force, which is my thrust force. As an output, I have the state vector, which is the tower position. Again, I'm using a 1 degree of freedom bending mode for this for the tower. The idea is if I know the position and velocity of the tower, I can actually find the bending moment in the tower. So it is a proxy for me getting those velocities. It's a proxy to get the tower bottom moment. So anyway, in the simple example, we have a mass spring damper. It's nonlinear through the force. It's easy to linearize if we assume that the force remains our only input. And we get this classical A and B matrices for such a mass spring damper system. And yeah, this is pretty much classic linear theory. At the end of the day, the only thing I want to point out to in my example here is the spectrum of my input. The spectrum I was using, so my input is the force, so it's SFF here on this plot. And I've been using what I call a banded noise input. So it's not white noise, that would be a constant input spectrum, but like a banded noise. It is not ideal, but it makes it easier to see what the product does. That's all I'm doing. So by having 1 and 0 here, you can see how the output spectrum is just cut by multiplying those two together. This is just a simple example to get familiar with the theory. But basically what we have, we can apply this to any spectrum of the input. It doesn't have to be a banded noise spectrum that I used here for simplicity. It can be any spectrum. It could be the spectrum of the wind. And it gives us the spectrum of our output directly. This is not exactly what we wanted. What we wanted was the probability density function. So how do you get from a spectrum to a probability density function? It's not easy. It's not really the same thing. And the good thing is at least the integral of the spectrum is the standard deviation. And we know that standard deviation is a good metric for fatigue. So maybe that's our one path forward. Some of the cons, other cons from this linear theory is the fact that it's limited to linear systems. And nonlinear relation, it's basically the same thing. It's difficult to do nonlinear relationships. Yeah. So then I was telling you, so the first path is the linear theory. Second path is the Ito equation, but I'm going to combine it with the Fokker-Planck because they are very close to each other. And also Ito equation is not what we are after. But to develop this stochastic theory, we start from the state equation that is of this form. And if the noise is white noise, so this is what I'm trying to represent here, but you know it's impossible to draw white noise in theory. If your input is this white noise, then you get into some stochastic math that I'm not super familiar with. And at the end of the day, you end up with a differential equation, which is a stochastic differential equation where your input is the white noise, very similar to this equation, because at the end of the day, this F is very close to this F, which we could integrate this stochastic equation, but we need dedicated solver. And if we integrate it, that means we basically do brute force approach. We have to do it for many samples. So that's not exactly what we wanted. But there's a counterpart to this equation. Once you have the Ito equation, you can figure out what is the Fokker-Planck equation. And this is the Fokker-Planck equation that relates, you can see this F mu that was here. So that's why it's related to the Ito equation and this sigma, which is a bit of a diffusion term that is also here in this equation, where basically this diffusion matrix is the 1/2 of the sigma transpose, and the sigma was showing up here. Sigma relates the inputs to the variation of the states. And what we have in this equation is the probability density function of our state, P. So it is a probability density function. It's multivariable, it's multi-dimensional. X can be any size of vector. And it gives us basically how the probability density function change as function of time. So if we know the PDF at t equals 0, we can find the probability density function of our states, all of our states at a given time in the future. So it's kind of hard to grasp. So how does it look like for our simple example that we had earlier? The F mu is very close to the state space model that we would have. I've just added in it the steady state force. And then I have a variation force. The part of the force that varies shows up in this, will be multiplied by this sigma matrix. So that's how it would look like for this simple case. Fokker-Planck equation is also not, no, it's manageable. We have only two states. We have Q and Q dot, the velocity and position of the tower. And so that's how the differential equation look like. And we use finite differences to actually solve this equation. That's kind of the downside of this approach is we go from an ordinary differential equation, which was our state equation, to a partial differential equation with respect to the probability density function. What's interesting to do, the first thing to do when we have such an equation is to look at a steady state solution, because things simplify. And in this case, we have a solution that is a multivariate Gaussian, just a B, two variable only. And we can figure out what is based on the constants of our system, we can figure out the standard deviation of this probability density function. We can plot it. So that's the solution after a very long time. That's how the position and velocity will look like after a very long time. What is this probability density function? So it's pretty interesting. And we can get, of course, the marginal distribution by integrating along one of the dimension. So if we want to extend this to a problem that is bigger than this 2 degree of freedom system that I was talking about, one thing we did right now is we implemented a finite element method solver. My colleague Corey did this at NREL using the Phoenix framework. It's a Python framework that deals with finite element methods, but this is only limited. If you do finite element, it's limited to 2D or 3D dimensions. But we use this to verify the steady state, that we get the steady state solution when we do this. So you can start with a probability density function that is not, that has some correlation between position and velocity. And basically, after a very long time, you don't have a correlation anymore between position and velocity. So that's something that you can verify with this finite element solver. We could use finite differences, but we have not done so. We could implement dedicated solvers to find a steady state. I think that's easier to do because then you don't have this time variable, and that would be probably the path forward I would choose for future work. The idea is, why do we care about the steady state? I think it's fair enough to say that we'll have enough information when we reach the steady state to kind of estimate the fatigue. That's my guess, at least. Before concluding, I just want to say we can also kind of try to loop back. We started with linear theory. What happens if we put a linear system into the Fokker-Planck equation? And we did this just as a simple exercise, and it turned out to be quite interesting. So now your F is just ax plus bu. Your Fokker-Planck equation, steady state, again, if you look at the steady state, so 0 on this side, ends up being simple enough. You can plug in a multivariate Gaussian into this equation. You have C here as the covariance matrix that relates the states to each other. And at the end of the day, if you plug this into the steady Fokker-Planck equation, you get what is called a Lyapunov equation that relates the A matrix and the B matrix to some extent, and the covariance matrix. Our unknown here is the covariance matrix. So we can solve for it by solving this equation. And then we know after a very long time, this will give us the correlation between the different state vectors. And then we'll know the probability density function of all of our states. So solving this equation, we get the PDF of all the states. And there's probably a way to link it to linear stochastic theory, but I haven't done this link yet between probability density function and spectrum. This is the link that I'm missing at the moment. So what are the pros and cons of this approach? It is what we wanted to do. So now we know how to do it. I've only dealt with states, but like the probability density of the states, but what we want is the probability density of the output. But it's not too difficult to put the output into your state vector. So it is achievable. It's quite easy to get the steady state, especially for linear system, as I was just saying. Again, some of the cons now is like we went from an ODE to a PDE. So that actually creates a problem when we try to do numerical integration, because the more states we have, the more difficult it is to integrate this PDE. So it is it seems to work fine for a few degrees of freedom. If we have thousands of degrees of freedom, or even if we have maybe 20 degrees of freedom, that's when we start to we'll have to give up on this method because it's going to be way too costly to implement. So that's the downside. I'm sure people will find ways, and there are some options in the literature to try to solve this what is called the curse of dimensionality, the fact that we have too many. All of a sudden, you're not in 3D, you are in 20 dimension. How do you solve a big problem in this dimension? So I'm sure methods will come to help on that aspect. Another limitation is the fact that I dealt with white noise input, my orange signal. And we know that inputs are not white noise, they have a given spectra. So how do we account for this in this theory? I think there are ways like you can do pink noise, you can do different kind of noise that maybe fits within this framework. But it'd be a next research question would be to figure out how to do any kind of spectra. I forgot, I have a comparison of results. So brute force approach, we do this 100 times. We look at what is the probability density function of the states and the position and velocity. We do it the Fokker-Planck way. We do it the linear theory way. And then we can get, the linear theory gets us the standard deviation. And then we fit a Gaussian with this standard deviation. And so this is how the results look like. So all the samples are in gray, all the different simulations for the probability density function of the position. In black, you have the sample average. In dash blue, you have the Fokker-Planck, and the dots that are maybe hard to see, they are on top of basically the Fokker-Planck. So that confirms that those two are in agreement. And that's it. So my conclusions so far, it was a proof of concept. Obviously, I used a reduced order, very simple model to do this. There's been some challenges, as I mentioned, the curse of dimensionality, the fact that it's going to be harder to do this for more degrees of freedom. The plus side is I think if we just want to get the steady state, then it's not that bad. The probability density function is probably not the full picture. If you want to understand fatigue, if you want to really get data that is important for, again, maybe operation and maintenance or for your design, the spectral content is important. So actually, linear theory gives us the spectral content. Fokker-Planck gives us the PDF. Can we find a way to figure out everything at once? White noise is limiting, as I was telling. Maybe we can do colored noise. And so, yeah, those are like potential path forward. And yeah, we published a tiny bit about it. Feel free to reach out if you have questions. And yeah, hopefully now we have time for questions. Thank you so much for your attention.
Well, thank you so much. I think that, we see all the virtual applause right now. So, that was a wonderful seminar. We thank you so much. We are ready for Q&A. So who would like to ask the first question? Judith, you turned your camera on. Did you have something to ask?
Yeah, no, thank you so much. I have done similar things purely empirically a long time ago. And so I have a lot of questions, but what I really would like to do is listen to the second part of your talk one more time. I typically, right, the spectrum is not related to the PDF, but it is actually the FFT of the autocorrelation function. And the autocorrelation function is obviously closely related to the PDF. So I wasn't completely sure what the problem there was. It might be a literature search, or maybe I didn't fully understand. But let me ask me a scientific question. So all this stochastic differential theory typically is valid for a time scale that is large enough so that your small scale nonlinear eddy-eddy interactions can be represented at noise. And so I know nothing about wind turbines, so I would be interested in the time scales of your problem.
I don't think I have so I think what you're pointing out is what I have in mind right now is when we do wind turbine simulation, we do them for a given wind speed, a mean wind speed, and then we have turbulence on top. And so we are in this part of the wind spectrum where we are, in turbulence part of it. And so the large scale, we always discard them in this approach. Whatever is larger scale than 10 minutes, we don't really care much about them, or we account for them differently through different design cases where we do extreme wind and things like this. So my short answer would be the scales we're looking at is really this, whatever turbulence scales we have in 10 minutes. Now, at the end of the day, I'm almost saying here that turbulence is Gaussian in that scale, which I know, expert in the field will complain about this. And so this is where having different kind of white noise, different kind of noise input would be maybe slightly better to have a better representation of what turbulence is. I don't know if that answers your question or if you have more. Actually, maybe you can tell me what you have in mind.
I'm happy to follow up, but maybe I wait if someone else has questions.
Sounds good. Sounds good.
I guess I'll go ahead and ask one. So the linear theory did quite well, but we all expect, atmospheric flow and its impacts on turbines to be nonlinear. The nonlinearity could become more important during extreme events, which may be what folks who are maintaining or building wind turbines care about most. Have you looked at extreme events and how well the linear theory works there?
No, I haven't, and I think that's a very fair point. Like you could expect way more displacement, way more nonlinearities showing up for those events. And you're right, if you care about tails of distribution, and you might get into trouble. So my way around this is really right now I'm trying to minimize the simulations when you are like maybe at operating conditions where for a given wind speed we have some nonlinearities, but it's not so you can probably get 90% of the results out with a linear model. That's my take. But you're 100% right that for extreme events, this is where this approach won't work.
Okay.
But I haven't got rid of the sampling problem fully because I think I want to do this wind speed per wind speed, right? So this is only like, if the mean wind speed is 10 meters per second, can we avoid doing like 20 simulation? Can we just do one probabilistic approach for this? So I'm not talking about the tail of the distribution of extreme events, and this is probably another kind of worms. Yeah.
Do we have any further questions? Okay, this was excellent. I certainly learned a lot. So I invite all of you to join us again next month. For our next on the second Wednesday. And I'm pulling up the next talk will be by Niels Norman Sorensen. And I think that will be a very interesting talk as well. So thanks everyone for joining us, and we look forward to seeing you next month. Take care. Bye-bye.
Thank you.
Thank you.